So today we're going to be doing Fluent Project 3, flow around a cylinder. And we're going to be doing 5 different versions of that with different Reynolds numbers in each one. So let's get started. Let's see, flow Fluent. We're going to set up our geometry by getting a new design modeler going. This always takes a couple minutes. And it's a 2D cylinder that we're doing. So we're just going to go on the XY plane. We're going to create our geometry here by creating a circle. And this circle is going to be 1 meter in diameter. Next, we'll set up our box, a rectangle. We will do this. Oops, I messed that up. Up here to undo. And I'm going to create a line that just goes all the way up. This is to help us with our geometry in our box. This 25 meters. Make this one 25 meters. And now we will draw our rectangle that we will enclose our cylinder with. Go to constraints, midpoint, and we'll make a box around our cylinder that's 50 meters by 50 meters. Now we'll get rid of our guidelines here. Okay, there's our box. Up here to concept, surface from sketches. Click here, apply, and generate. And there is our cylinder right there. Okay, back. We are going to set up our mesh. And we should have 2 here. This one can go right here. Screw this off. Okay, first things first. Create mesh, insert a method, apply, home, generate. Triangles. I'm going to use triangles right there. And now we'll go into sizing. Let's see here. We got to move some of this stuff around. We're going to select an edge here. Apply. Element size, number of divisions. We're going to go 200. 200. We're going to capture curvature. We're going to turn that off. No. And we're going to make our behavior hard. And generate. Okay. After that, we go into mesh. We will insert inflation. And we will select the face. Apply. One face. Geometry selection. Geometry selection right here. Apply. Smooth transition. First layer thickness. We'll do, I think it's 0.003. 0.003 for first layer height. Maximum layer 65 to 1.2 and home and generate right here. Okay. Go back here to mesh. Oops. Let's make our element size 0.1515, and we will generate here and generate. This takes a second, but we can see around our cylinder, our mesh is looking really tight, and that's what we want. And this is just taking a minute. And there we go. And here's our mesh. We got some good mesh going on here. Okay, let's name our sides. And this will be our velocity inlet. Inlet. Here's our pressure outlet. And as in our previous projects, our top and bottom will be symmetry. Okay. And we've got to name our cylinder here. And that will be wall. Wall, okay. All right, our mesh is complete. Come back here, let's update our mesh. And everything looks good. Okay. Cancel this out and let's go to setup. We will do double precision and we will have 4 processes do this. And for our first case, we're going to have a Reynolds number of less than 1, and we will have a viscosity of 0.05 kilograms per meter second. We'll have a fluid velocity of 0.025 meters per second. All right, let's go here to models. A Reynolds number with less than 1 is very extremely laminar, so we'll make this laminar. Right here, our viscosity, materials, fluid, air. We have for our Reynolds number to be less than 1, we're going to use a Reynolds number of 0.5. We're going to use a density of 1, and our viscosity will be 0.05 kilogram per meter seconds. Change, create, close. Okay, we just want to make sure our surface body fluid is air, and it is right there. Close. Okay, boundary conditions. Our pressure outlet, we have a pressure outlet's fine there. Our velocity inlet is here. Let's go to edit. We set our air velocity at 0.025 meters per second. Extremely slow. Apply, close. Okay, our reference values will be computing from the velocity inlet. We have our areas at 1, densities 1, depth 1. Everything looks good here. Velocity 0.025, viscosity. Okay, everything looks great. We want to report definitions. We are going to report our force report. We want our drag forces reported. We're going to have our drag coefficient. We're going to print it to console. And okay. And that works. Okay, and then we come down here to initialization. More settings, we're going to go to 25 right here. Okay, and initialize. Oh, whoops, I forgot to do this. Well, okay, there we go. Now we have report definitions up there. Okay, close. Okay, initialization is done. Let's go to calculations. Um, Number of iterations, we'll do 500. The lower Reynolds numbers, they seem to go pretty quick. And calculate. Maybe not. And this takes a while, actually. I thought 500 might go a little quicker. I've seen where it's been at 1,000 and it'd take 20, 30 minutes, and those are in higher Reynolds numbers as well. So, but moving right along, I think from now on we'll do iterate like 100 iterations. We're slowly getting there. We're halfway there. It's 80%. 90%. And it's finished. Hooray. Okay, first thing we want to do is we're going to come over here to our report definition. and we're going to compute. Okay, and you can see right here that we have a drag coefficient of 21.42. So we'll come over here and we're going to check out our reports, our forces right here for that wall, print out the forces for the wall, and our total forces, our drag force is going to be 0.00669, it looks like, newtons. Okay, so we're done with this. Let's see. Let's close this out and we will go back to here and let's wait for that to close so we don't have licensing issues. And let's go to results. And here are results. Where this off here. Let's move this on over here. And first thing we're going to do is check our streamlines. Okay, we will start from the velocity inlet. Let's do let's do 750. 750 streamlines, velocity streamlines. And here we are. You can see it's very slow moving. But those are good streamlines around our cylinder. All right, let's take our default legend here. Let's go to horizontal appearance. Let's make this one. Oops. One. Let's make this 0.05. Precision looks good. Scientific fixed and apply. Okay. Now, let's turn our streamline off. Let's get our contours here. Location symmetry 1. We'll go with velocity here. Let's try velocity U once and see what this looks like. And then contours 500. Apply. Not very much there. See what velocity does for us here. Let's apply. Extremely blue. And we have some kind of on the pressure outlet out there. Got a little bit of color change. Now let's look at pressure. Symmetry 1. Okay, 500 and apply. And not a lot of pressure going on here. Like I said, very slow speeds, very small Reynolds number. Okay, so let's try another one. Let's see here. Let's close this out. Let's go back to here. Now let's set up, let's duplicate our cylinder and let's try it again. Okay, let's see this one. This was RE number less than 1. So we'll go RE number equals 0.5. Okay, this one, our Reynolds number is going to be 40. Number equals 40. Okay, and let's go to solution. Here, and it's thinking again. For this particular case, we're going to be using viscosity of 0.5 kilograms per meter second. And we're going to have a fluid flow of 20 meters per second for velocity. Done. Okay, so let's come back up here. We're still at laminar. Material, fluid, air here. Okay. We have a constant. We're going to change this to 0.5. That's our viscosity. Create, close. Okay. Boundary conditions. See our pressure outlets, pressure outlet, velocity inlet. Let's edit this because we want our velocity at 20 meters per second. And apply, close. All right. Reference values from velocity inlet, 20 meters per second, 0.5. Everything else looks good. We're going to get rid of this old report and we will get a new report specifically for this Reynolds number. Force report, we want our drag coefficients. We're going to print to console and we're going to do it with our wall. Okay, and close and initialization. We're still at 25. Okay, initialize. In solution data, import files. You want to discard the data and receive it? Yes. So we will reinitialize everything at our new parameters. That is done. Let's run calculation, automatic. This time we're going 100 iterations to save time. And calculate. Goes a little bit quicker. That was way quicker. Thank you. All right. Let's look at our report definition here. We're going to compute. And for this one, you can see right here, we have a drag coefficient of 1.53. And let's come down here to our reports. Let's check out our forces and print. Whoops, wall and print. Here we go. And you can see we have a drag force of 306.44 newtons. Viscous force is at 105. Pressure force is at 200. Okay, let's close this out. Yes, and let's head back. The workbench and let's get our results. Get these contours here. Whoops. Contours here. Let's shut down contour 1. Let's go to streamlines, streamline 2. We'll start from velocity inlet. And let's do 500 again. And here, equally spaced and apply. And here we go. Oops. And this is our streamline at Reynolds number equal 40. And it doesn't look bad. Let's shut this off. Let's look at some contours here. Contour 2. Let's see. Symmetry 1. Let's see, pressure. We're going to go with velocity here first. contours 500 and apply. And there it is. It doesn't look too bad. Let's see, let's try pressure. Let's see, pressure, global 500. Or if we did symmetry too, that would change anything here. It's kind of a weird thing. Try symmetry one once. Apply. Looks the same. Okay, so that's that particular Reynolds number 40. Let's close this out. Let's go back here. Let's duplicate this again. And this time we're going to go for a Reynolds number of 150. Let's see here. Okay. RE number equals 150. Okay, let's go to solution. For Reynolds number of 150, we'll be using a viscosity of 0.33 kilograms per meter second, and we'll have a flow velocity of 50 meters per second. The computer's been getting a workout this week, and it's running a little slow. You can tell it's tired. Okay, let's go back to models. Still at laminar. Materials, we're going to go with air here. And we're still at a density of 1. The viscosity will be changed 0.33. Something like that. And close. We'll come down here to our boundary conditions. Our pressure outlet's still the same. Velocity inlet, let's edit it because we need 50 meters per second. Right here, meters per second, apply. Close, and let's come down here to reference values from velocity inlet, put inletty. Okay, 50 meters per second. There's our viscosity and reports. Let's see, we're going to be doing, let's get rid of this one. And let's start a new one. For a new Reynolds number, let's see, force report, drag force, drag coefficient, and print to console, the wall, okay, close, come down here to initialization, our settings 25 is good, initialize, okay, reinitializing here, that is complete. Let's run our calculations at 100 iterations just for time's sake and calculate. Calculations complete. All right, let's come up here. Let's check out our report definitions here. Let's compute. Okay. And you can see we have a drag coefficient of 0.9398, I guess. And Let's look at our reports, courses on the wall. Let's print these out. And here you can see with our higher velocity, our higher, a little bit higher Reynolds number, we have a drag force of 1,174.73. All right, so that said, let's clear this out. Let's go back to Workbench and let's go to results. Last ones, let's see here, shut the contour off. All right, and let's come up here. Let's go to Streamlines. Streamline 3, okay. Start from velocity and lettys I put on there. Really spaced. Put 500 again. And apply. There it is. Not a bad streamline. And let's see, let's go to contours. Contour 3. And we'll start off with velocity. For some reason, I like to start off with velocity. Symmetry 1. 500. Apply. Oops. And not bad. It's very cool. Okay, I mean, you can see the separation in the middle, see the separation on the outsides. Okay, let's try pressure here. Let's go with pressure and apply. And once again, we just kind of, the pressure seems to be right on the face of the cylinder, um, with lower pressures around the side and obviously behind. Okay, so let's go to our fourth case and come back to Workbench here, and let's come up here, duplicate again. Now let's just come over here. Let's come down here. Let's just go to solution here. Now for case D, we're going to have a Reynolds number of 50,000. Calls for it to be greater than 4,000 and less than 300,000. So we're going to go with 50,000. For this, for Reynolds number of 50,000, we need a viscosity of 0.0006 kilograms per meter second. And we're going to have a flow velocity of 30 meters per second. Okay, so here we go. Models, we're still going laminar because it's external flow. And okay, so here are our properties for air. Still have air density at 1 kilograms per meter cubed. We are going 0.0006 kilograms per meter second on viscosity. Big flows, boundary conditions. Here we go. Pressure outlet, still have pressure outlet, velocity inlet. Let's edit this because we want our velocity at 30 meters per second. 30 meters per second. Apply. Close. Reference values. We'll be doing this from the velocity inlet. Here, everything looks good. 30 meters per second, 0.006. Excellent. And report definitions. Again, let's delete the old one. Yes, and let's get a new one going here. New under force reports, drag force coefficients. Into console. That wall going. Okay. All right. And now we will go to, let's close this out. Let's go to initialization. We want to make sure we're at 25. That's correct. Initialize. Okay. And here we start our initialization. We're complete and run calculation. We're going with 100 again for time's sake. And calculate. And it starts to go wonky as these higher Reynolds numbers. It is kind of maintaining its linearity, which is nice. I've seen them where they've gone completely bonkers, up and down, and your contours and your streamlines, they start to look really crazy. Your velocity profile, it looks weird. For the most part, this one's, it's getting wonky at the end here. Yeah, there it goes crazy. And so let's check out our report here. Compute. Okay. And we get a drag force of 0.603. Come down here to our forces, our reports, and go to forces. Try this here, wall. Let's print this out. And we're getting a drag force of 271.32. Okay, let's see here. Let's close this out right here. Let's go back to workbench. And let's go to results. Okay, let's shut these. Shut contour one down. Let's come up here. Let's move this stuff over. Let's go to streamlines. Streamline. Oh, we'll call this RE equals 50,000. Okay. And oops. Velocity inlet. Streamlines, we're going 500. Velocity forward and apply. And starts looking crazy. I don't know why this did that like that. Unless we redid it. Back to the normal. Let's look at our let's shut this off here. Let's go with contours. Okay, contour two. Let's see here. Let's go with symmetry one. Let's go with pressure. Well, we start off with velocity like we always do. 100 and apply. Just weird. It's from those, I think it's from ran our calculations. Um, it just looks it's awkward. It doesn't look right. Let's see what our pressure does here. apply. Yeah, it doesn't look right. Um, can try and redo it. Let's go back to workbench. Bench here. Let's start a whole new fluid flow fluent here. Let's start with our geometry. Let's do it again. Get it this time. XY plane. Let's go to sketching. Let's go to circle. And let's go like this. Dimensions. 1 meter. 1, enter. Okay. Back to drawing, line. Let's go to there. To there. Let's go back to drawing dimensions here. This one is going to be 25 meters. And this one again, 25 meters. Okay. Let's draw a rectangle. Boom. Back to dimensions. This one goes, whoops, no, we don't want that. We want constraints. Midpoint. This midpoint's going to coincide with that one. This midpoint's going to coincide with that one, and we have our perfect spots. Okay, back to drawing. Let's get rid of these right here. Okay. Concept, surface from sketches. Click there, apply, generate. There's our circle right there. Okay. We go back here. Let's go to mesh. And get rid of this one. Oh, we've got an error. I think it crashed. Let's try it again. We've had another error. Oh, maybe not. There it is. Okay. All right. So let's go here. Insert method, face. I'm going to apply one face. Go down to here, triangles, and home, generate. Okay. Mesh, insert sizing. Let's come up here. Edge. Let's go in here. Let's click the edge there. Apply one edge. Element size, number of divisions. We'll go 200. And capture curvature. No. We want our behavior to be hard. Home and generate. And now we'll go to mesh, insert, inflation, type of base, apply, boundary selection, right there, apply one edge, smooth transition. We're gonna go first layer thickness, 0.003. This is gonna be 65. Come up here and generate. Okay. It's a minute. Now, first layer height. We're going to come back up here now. This is going to be 0.05, I believe. 0.015. 0.15. Okay. Generate. There we go. Takes a second. Our mesh. Mesh looks nice. All right. Let's name our sides. Velocity. Inlet. Okay. And let's go over here and pressure outlet. Okay. And boom, boom, and essentially. Okay. And of course, we're going to name the inside of our wall here. There it is. Wall. Okay. All right. Now we'll come back to here. Update mesh. Mesh has been updated. Boom. Let's cancel that out and set up. So again, double precision. Go 4 processes and start. For this last case, we're going to do a Reynolds number of 500,000. That is a turbulent. For external flow, that will be considered turbulent flow. So we'll come up here to our models. We will do K epsilon, standard K epsilon for turbulent flow, fluid, air. We'll continue to use 1 as our viscosity, or for our density. Our viscosity is going to be 8 times 10 to the negative 5th. 8. And flows. Okay, our boundary conditions. Pressure outlet is good. Velocity inlet, edit. So our velocity magnitude will have a velocity of 40 meters per second. 40 meters per second. Apply. Close. Okay. Reference values from velocity inlet right here. Looks good. 40 meters per second. 8 to the negative 5th. Okay. Port definitions. We would definitely like a report on drag forces. Do it to our wall here, print the console. Okay. Close that out. Initialization. Move to 25. There. Initialize. Okay, initialization is complete. On our calculations, we are going to run 100 iterations 4 times sake and calculate. And here we go. Calculations complete. Okay, let's go check our report definitions here and we'll compute. Okay, we have a drag coefficient of 0.358. And let's come down here to our forces, our reports. And let's see here on our wall. Let's print these out and close. We have a drag force of 286.3553. All right. Our viscous forces are very, very small because our viscosity is very low. But you can see our pressure forces. They are the main driving force for our total drag force. Okay, let's close this out. Okay, let's go back to Workbench. And let's go to results. As soon as all that closes out. There you go. And square this off. Move this over here. Let's look at our streamlines first and foremost. Okay, velocity or velocity inlet equally space. Let's go 500. And apply. Let's try 1500. Let's see if this looks any better. Apply. Yeah, you can see a little bit of streamline. Velocity increases. It changes legend here to horizontal. Here it's 1.05. Scientific fixed. Apply. And you can see it's right there. Okay, let's go to go check out our contours and symmetry 1. Let's go with velocity. Let's go with 7. And this one just to play around. Yeah, there's our velocity profile right there. Let's check out our pressure. So, and it looks like our other ones. Our pressure in the front, lower pressures here, and you get pressure. So that's pretty much it. There's 5 cases of 5 different Reynolds numbers showing how to do Ansys Fluent fluid flow over a cylinder. Have a great day. And